In this video, we are going to see about magnetic forces, which is in module 4. So before discussing magnetic forces, let's see one general example. That is, if you consider the wind that is moving air, right? Assume this is the wind which is moving in this direction. If we keep one object here, this object will move in this direction with some amount of force. So this is the general example that what we have known very well. Now consider an electric field. The electric field is in this direction. The electric field is in this direction. Now if we keep one charge somewhere here, this charge Q definitely will experience some amount of force due to the electric field. This charge will move in this direction, that is electric field direction only. So therefore force experienced by the charge Q due to the electric field is Fe, that is E stands for electric field. Fe is equal to Q into E bar. Now consider the magnetic field. The magnetic field is always in the closed path. Why it is always in the closed path means general example is consider one magnet. For the magnet, one side if the field is emitted means the other side the same field will be terminated. Whatever the side the field is emitting, that is called as a north pole. Whatever the field that is absorbing, that side is called as a south pole. So therefore here the field is magnetic field is always having a closed path. So therefore here consider the magnetic field which is in the closed path. Now consider one region, say this is the region. In this region the magnetic flux density is B bar. Now in this region if we keep the charge Q, definitely the charge Q will move with some velocity E bar and making some angle with respect to the flux density, that is B bar. So therefore that angle is represented by theta. The angle is theta is the angle between the magnetic flux density and the velocity V bar. Now the force experienced by the charge Q is F suffix M. M stands for magnetic field. In the previous case, E stands for electric field. Force experienced by the charge Q is equal to charge Q into B bar V bar sin theta. So this can be rewritten as this as per vector algebra, which looks like A bar B bar sin theta. A bar B bar sin theta can be written as A bar cross B bar. So here it can be written as a B bar cross E bar. So total force experienced by the charge Q which is placed in the electric field as well as the magnetic field, F is equal to F E bar plus F M bar. F E bar is Q E bar plus Q B bar cross V bar. Take Q is the common, then here it is E bar plus B bar into E bar. This is the total force due to the electric field as well as the magnetic field. If the magnetic field is 0 means force F is equal to Q into E bar only. If the electric field is 0 means force is equal to Q bar B bar cross V bar. So depending on the field present in the system, we can consider either this equation or this equation or this equation. It is a general analysis. Now let's see here the force on a moving point charge which is placed in the both electric field as well as the magnetic field. Now let's see here force on a moving point charge. So this is also called as a Lorentz force equation. To analyze this one here, we need to consider two fields. One is electric field, another one is the magnetic field. In the both fields, if the charge Q is placed, what is the total force experienced by the charge Q? Okay, now let's see here. If there is a charge or moving point charge Q in an electric field E bar, then there exists a force on the charge. Force is given by F suffix E bar, that is force due to the electric field is equal to Q into E bar. This is the electric field which is in this electric field charge q is placed. This charge q will move in this electric field direction with some velocity. So therefore here force experienced by this charge in the electric field is F E bar is equal to Q into E bar. So this force is also called electric force and its direction is same as the direction of E bar. Now if the same charge Q is placed in magnetic field, let's say what is a mathematical equation, that is the force experienced by the charge due to the magnetic field. If the same charge, that is whatever the charge is considered in the previous case, is placed in a steady magnetic field, it experiences a force when it is moving. When it is moving. So this force is a function of charge q moving at a velocity v and the magnetic flux density and the sign of the angle between the velocity and the v bar. So if it is a velocity, if this is a v bar, the force will be in this direction. So the force experienced by the charge in the magnetic field, that is F suffix m, m stands for magnetic field, is equal to product of charge q, velocity and flux density, sign of the angle between the velocity and the v bar. So here v b sin theta can be written as a v bar cross b bar, that is a b sin theta can be written as a bar cross b bar. So therefore Fm is equal to q of v bar cross b bar. So it is equation 2. Now the total force on a moving charge in the presence of both electric field as well as the magnetic field is given by F is equal to summation of electric field force as well as magnetic field force. Electric field force is Q E bar, magnetic field force is Q of V bar cross B bar. So therefore F is equal to, take Q is the common, E bar cross E bar plus V bar cross B bar. This is the complete force, total force due to electric field as well as the magnetic field due to the presence of electric field and magnetic field. This equation is also called as a Lorentz force equation. So in this equation, if the electric field only present but magnetic field is not present, means this term will vanish. So therefore F is equal to Q U bar. If electric field is not present, only magnetic field is present, means this term will be vanished. F is equal to Q into V bar cross V bar. Depending on the presence of the electric field or magnetic field, we need to consider this term or this term. If both are present, means then this complete equation is valid for determining the force on the charge which is placed in electric field as well as the magnetic field. So this equation is called as a Lorentz force equation, which relates the mechanical force to the electrical force. The applications of Lorentz force equation is for accelerating the particles, right? This type of concepts are useful. That is the major applications of the Lorentz force equation, and here this is due to the force on a moving point charge which is placed in the electric field as well as the magnetic field. So ultimately the final equation is F bar is equal to Q of electric field E bar plus V bar cross B bar. V means velocity and B means magnetic flux density. This is about Lorentz force equation. Next we are going to see force on a differential current element. So to